Sometimes in science, we guess something exists before we can actually prove it. A good example is gravitational waves. Einstein thought they existed in 1916, but we only found them 100 years later. The same thing happened with atoms. Back in the 1800s, people believed in tiny particles called atoms. But it wasn't until the 1900s that we really understood them thanks to the new science ideas. Both theories shows that sometimes scientists need to wait a long time to prove their ideas right, but they keep trying until they find the answers. This journey of guessing and then finding out for sure is what makes science exciting. Even if it is really a long time, scientists don't give up. They keep asking questions, doing experiments, and using tools to see what we can't see with our eyes. Just like detectives trying to solve a mystery, scientists look for clues everywhere. Sometimes they might be on the right track, but the tools or method to prove their ideas might not exist yet. But as the time goes on and the technology gets better, things that were once invisible or unknown can be discovered and understood. It reminds us that in science, being patient and curious is super important. Even if we don't have all the answers today, we might find them tomorrow or maybe in 100 years. In the previous video, we talked about two distinct ideas of nature of matter in ancient Greece, about the atomic theory of Democritus and four elements of Aristotle. And for 1500 years, we were not advanced enough to confirm which theory was correct. In fact, four-element theory eventually showed inconsistencies with the early experiment in 17th century, which we are going to tell the story of it as the story of modern chemistry. But the long time in between the proposal of atomic theory from ancient Greece to the time that we know as modern chemistry, there was a huge gap, and this gap was fulfilled by alchemy. Different alchemists had different opinion about nature of matter. Some of them believed in atomic theory, and some of them believed in four-element theory. But they were trying to do basic chemistry, not with the goal that we are following today in science. They were following some form of proto-science ideas. From the economic standard, they were trying to turn copper into gold, and some of them were looking for the elixir of life to stop aging. But with all of those goals and purposes, they developed a phenomenological understanding of chemistry. They practiced a lot of chemical techniques to handle the liquids, practicing medicine with the human body. They were basically forming the foundation of modern chemistry, and most of them were not really aware of nature of matter at that time, but they just had an understanding what matter does to human body or other properties of it. The known figures at the time were Al-Razi, Jabir bin Hayyan, and Isaac Newton. We know Newton as a founder of mechanics and a lot of branches of mathematics, but unfortunately he was not a very successful chemist or even alchemist, but he was practicing it. At the same time with Isaac Newton, Robert Boyle was living in England, and in contrast with Newton, he was a scientist in the field of chemistry. He was one of the pioneers in the field who turned alchemy into a genuine science, and he's mostly renowned for recognizing Boyle's law, indicating the inverse relationship between the pressure and the volume of the gases. Joseph Priestley was also an English chemist, and he's mostly known as the person who discovered oxygen. He actually isolated the oxygen gas from heating up mercuric oxide. We need to mention before Priestley a Swedish chemist named Carl Wilhelm Scheele. He was the person who actually isolated oxygen 2 years sooner than Priestley, but he published after him. And they both isolated oxygen in a different and independent ways. But why? They were looking for isolating oxygen? Because one of the active fields of study at that time was studying combustion. People wanted to know why combustion takes place, why some materials burn better than the other ones. At the same time, there was a proto-theory named phlogiston theory. It was like anything that is burned, make phlogiston out of it, which they probably thought it's the flame of the fire. Well, they didn't know about plasma or those things at that time, but they were thinking some mysterious material is coming out when things are burning. At the same time with Priestley and Scheele, Antoine Lavoisier was also doing chemical experiment in France. He's one of those people who transformed chemistry and revolutionized it, like Albert Einstein to physics. He was one of the pioneers of measuring the mass during a chemical reaction. He was basically keeping the gas from burning before and after the chemical reaction, and he realized the mass of the compounds are the same. That was the first indication of the idea that mass or matter neither created or destroyed in a chemical reaction. Both Scheele and Priestley believed in the phlogiston theory. Phlogiston theory was basically saying the lack of phlogiston makes things burn better. So when things are burning, they're producing phlogiston out of them. He was the first person who said there is no dephlogisticated air. He called this new element oxy from the Greek word which means sharp. He mistakenly thought at that time that oxygen is the element which makes acid to be very reactive at that time. Later on we realized that's basically hydrogen, not oxygen. But anyway, he called it oxy, which means sharp and reactive. The story of the air that we breathe in ends with two other discoveries at the same time in England by other two chemists. Now I want to tell you the story of carbon dioxide and nitrogen discovery in the 19th century by Joseph Black and Daniel Rutherford. Starting from Joseph Black, he was mostly working on the heat capacity and the thermodynamic of his time. He is best known for his pioneering work in measuring the heat capacity of the materials. Heat capacity is basically showing the response of the temperature change of an object relative to the heat energy that we are giving it to the object. Some of the materials like metals have a very low heat capacity, which means that you can change their temperature easily without adding too much heat to it. And some of the materials have a very high heat capacity, which means that you have to give a lot of heat in order to raise the temperature of them. But the most important discovery that he made was the discovery of a gas which was in the air. Again, we said there was a long history about the air. We didn't know at the beginning that there was several compounds and elements in the air that we are breathing in. In the combustion theorem and the story of the oxygen, we realized one part of the gas that we are breathing is the oxygen. But what are the other parts? Because simple observation was that plants are doing something in reverse of human and animal breathing. So what he was doing was to heating up some of the calcium carbonated compounds which we can get from the rocks or mineral materials, and the gas which was releasing from those compounds, it was pretty useful for the plants to do the photosynthesis. He also realized that carbon dioxide in contrast with oxygen is not good for combustion. Joseph Black was also a believer in the phlogiston theory. So again, he didn't realize that he discovered the new compounds because carbon dioxide is a molecule, not the element, but he was thinking of it as something related to the phlogiston theory. It was sooner or later realized by people that this is basically carbon dioxide, which means a compound from mixing carbon and oxygen, which were known then independently. Carbon was discovered for a long time and oxygen was discovered by Lavoisier, and people realized carbon dioxide is simply a mixture of them. Joseph Black had a student and his name was Daniel Rutherford, and he discovered nitrogen. He actually didn't name it, but he mostly founded his works on Black's work on heat capacity and the theory of combustion. He isolated nitrogen by filtering out the carbon dioxide and oxygen out of it. He conducted an experiment in which he trapped a mouse in a confined volume of the air until it died, and then he burned the candle in the remaining air until it went out. Rutherford then thought that these two processes, respiration of the mouse and the burning of the candle, consume only certain components of the air. He then tried to burn phosphorus in the remaining gas, but it did not support combustion. Rutherford also found that the remaining gas would not support life. However, this residual gas was made up a significant portion of the volume of the original air, which led Rutherford to the conclusion that he had discovered a new non-reactive component of the air. It is important to note that Rutherford did not call this gas nitrogen. He initially called it noxious air or phlogisticated air, terms that related to the phlogiston theory. It was only later that the element was given its current name, nitrogen, by Chaptal. The law of definite proportions states that a given chemical compound always contains the same proportion of elements by mass, regardless of the source of the compounds or its method of preparation. While this law seems obvious to us now, it was revolutionary during its time and played a pivotal role in establishing modern atomic theory. Joseph Proust, a French chemist, is primarily associated with this law due to his extensive work on the composition of various compounds. Proust's assertion about the fixed proportion of elements in chemical compounds was based on his experimental studies, especially those concerning the composition of copper carbonate and other copper compounds. Despite his finding, he faced opposition, particularly from Berthollet, who believed in variable composition for compounds. However, over time, Proust's observation gained acceptance, and the law of definite proportion became fundamental to chemistry. It was Proust's work that formed the basis of the law. Jacob Berzelius, a Swedish chemist, played a very important role in the development of modern chemical notation, elementary analysis, and the theory. While Berzelius is not directly credited with proposing the law of definite proportions, his work in elementary analysis and his advocacy for Proust's findings reinforced the law. Berzelius' contribution helped the law of definite proportion as a fundamental principle in chemistry. The law of definite proportion, or constant composition, implies that the specific compounds will always contain the same proportion of elements by mass. This consistency hinted toward a deeper and more fundamental structure of matter, which eventually led to the atomic theory. Here's how the fixed ratio in compounds pointed toward the idea of atom. When early chemists began analyzing compounds, they found that the ratio of the elements in those compounds were often simple whole numbers. For example, water always had a ratio of hydrogen to oxygen by the mass of 1 to 8. This simplicity was difficult to explain if the substance were made of continuously divisible amount of elements. And the consistent ratios, no matter where a compound came from or how it was made, it had the same composition by mass. For instance, whether water was collected from river or lake or produced by burning hydrogen and oxygen together, its composition remained 1 to 8 by mass. Such a consistent ratio implies a fixed and fundamental structure. So there is one thing missing in the law of definite proportion to be the atomic theory or modern atomic theory. This is the effect of atomic mass. For example, we said in the water, the ratio of oxygen to hydrogen is 8 to 1. But this is mostly because of the higher mass of oxygen compared to the hydrogen. So 1 to 8 is not the right ratio that we are looking at. So for this reason, we have to go to multiple compounds from two elements and calculate the ratio of the same element in order to take out the effect of atomic mass. And this is the law of multiple proportion by John Dalton. John Dalton was an English chemist and metrologist who is best known for his pioneering work in the development of modern atomic theory. This theory was based on several postulates. First, elements are made of tiny, indivisible particles called atoms, simply similar to ancient Greece. Atoms of a given element are identical in mass and properties. Atoms of different elements differ in mass and properties. Atoms combine in simple whole number ratio to form compounds, and atoms cannot be created, divided, or destroyed in a chemical reaction. They simply rearrange. But what observation led him into that conclusion? The law of multiple proportion. This law states that when two elements form more than one compound, for example, carbon monoxide and carbon dioxide, the ratio of the masses of one element that combine with the fixed mass of the other element are ratios of a small whole number. This observation was crucial in supporting and developing the atomic theory. While the law of definite proportion emphasizes the fixed ratio in which elements combine to form specific compounds, the law of multiple proportion focuses on the different ratios in which the same element can combine to form different compounds. The former gives insight into the composition of a specific compounds, while the later one provides a broader view of how elements can variably combine to yield different compounds. Both laws, when observed together, provide compelling evidence for the existence of atoms and the idea that they combine in simple, definite ratios to form compounds. Again, consider carbon and oxygen. They can combine to form carbon monoxide and carbon dioxide. In CO, 12 grams of carbon combined with 16 grams of oxygen. In CO2, 12 grams of carbon combined with 32 grams of oxygen. The ratio of oxygen masses, 16 grams, 32 grams, is simply 1 to 2. This suggests that the compounds are formed from atoms in specific discrete ratios. It was somehow the reverse of the definite proportion. In definite proportion, we were breaking the compounds to find the ratio of the masses of them, but in this way, we are calculating the ratio of the masses of the same element in two different compounds. So that was a summary of what happened in almost 100 years. That is how at the beginning of 19th century, we guessed the existence of the atom based on some physical evidences from chemistry. But still 100 years of development was needed for physicists to understand the structure of the atom. They realized the atom is not indivisible, but it's mostly responsible for the chemical reaction. So hopefully we are going to get into that part in the next episodes. Thank you so much for watching this video.